Welcome back to part 2 of the visual system. In the last video, we talked about what the eye looks like and about the different parts of the eye, as well as rods versus cones. In this video, we're going to talk about how we use all of that information in order to process visual information. So the first thing we're going to talk about is dark adaptation. So this is the process in which the eye becomes more sensitive to light in low illumination. In other words, if you've ever noticed that you're sitting in a dark room and then you go outside and the sun is so bright and it hurts your eyes so bad, when before the sun, it's the same sun, it didn't hurt before, but it's because you became adapted to the dark. That's what this happens. So dark adaptation is complete in about 30 minutes. So you'll see this when you sit in the dark for about 30 minutes. That's the best way to see this. So, if you're bored and want to try this, go ahead and do it. What else is there to do in quarantine? Now, sometimes you can see this happen after just 10 minutes in the dark, and that's because most of this adaptation happens in the first 10 minutes, but then it does take a little bit more time, about another 20 minutes, for this adaptation to kick in to full effect. So if we look at this graph over here on the right side, then on the x-axis we have time in the dark in minutes, and then on the y-axis we have the intensity of light to produce vision. Okay? So pretty much the first time you go into a dark room, you're not going to be able to see a lot, right? Because your eyes are used to the light. So your cones are going to be doing most of the work. And it takes about 10 minutes for your eyes to become adjusted to the dark so that you can see well in the dark. And so your cones are going to stop they're going to stop doing their work, and that's where the rods kick in. And you're going to start using just your rods to see instead of your cones in these next 20 minutes. And after 30 minutes, you're going to be able to see pretty well in the dark, assuming there's a little bit of light. Now, if it's complete blackout, there's no light at all, you still can't see, but as long as there's a little bit of light, your eyes will be able to adjust and you'll be able to see pretty good in the dark after 30 minutes, thanks to using just your rods. Now, again, if you were to go into the sun after this 30 minutes, or even after 10 minutes, you'll see this a little bit, but 30 minutes is ideal, then you're still going to be using just your rods and not your cones. So you're going to step into the sun, and there's going to be way too much light for your cones or for your rods to process. So it's going to take a while for your cones to kick back in, for your cones to start working again, because your rods will be the ones that are kind of awake and working, and your cones are kind of on a break. So that's why it's going to take a while. Now, let's talk about seeing color. So remember that cones are the receptor cell that processes color or helps with seeing color. Now, there are 3 properties of light that help influence the perception of color. So we talked about these a little bit in the last video, but the first one is wavelengths, and this tells us hue or what color. So like red or blue. The second one is amplitude, and this tells us the brightness. And then the third property is purity. So this tells us the saturation. Now, when talking about saturation, if we look at this fun little pie over here, saturation means like how deep the color is. So from like a light blue here to a darker blue, the amount of saturation, okay? So if you think of, you have a white base, how much of that color is it to get away from white. And that's what saturation is. So here we have a light yellow to a dark yellow, and so a dark yellow has more saturation. And then yellow versus blue, that would be different hue or different wavelengths. And then brightness, so going from like a dark black to a lighter color would be brightness. So take the same color, look at it in sunlight, look at it in a dark room. They're going to have that paper, that color you're looking at, is going to have the same saturation and hue no matter where you are, but it's going to have a different value or a different brightness based on the light that you're seeing. Now, you can mix colors, of course. That's how we get different colors. So there's additive color mixing or subtractive color mixing. So there's two different types of color mixing when we're talking about light. So additive color mixing superimposes lights, putting more light into the mixture than exists in any one light by itself. In other words, you're taking two lights of different wavelengths and overlapping them, and you will end up with perceiving a color of like an additive wavelengths. Okay, so if you take, if you have like a red light and a yellow light, and you shine them both overlapping on a white piece of paper, the color you're going to perceive would be like a yellow, because you're adding those together. There's also a subtractive color mixing, so this removes some wavelengths of light, leaving less light than was originally there. So this one's a little harder to explain, but we're going to try. So additive color mixing, so this is more with lights. So again, we have different colors and you're adding the wavelengths together. Of course, when you're adding light, then pure light or the highest color would be white light. So when you add all three colors of light together, you end up with white. But then if you add, say, just blue and green, then we get this kind of in-between color. Or if this is like a purple, violet light and a green light, you get a blue. If you add green and red, you get yellow. But if you add all three colors, then you get white. Okay? Because remember, with light, there's three colors of light. You have red, blue, and green. And together they make white. Whereas with subtractive color mixing, this is more like when you're talking about color pigment, so like paints and stuff. And so there's three primary colors with that: red, blue, and yellow. So notice they're different. And when you mix all three together, you end up with black. And so that's subtractive color mixing, because black has a smaller wavelength than all these colors, right? So white has a higher wavelength, black has a lower wavelength. Now, there's the Trichromatic Theory. So this is an important theory when talking about light and vision. And this is that the human eye has three types of receptors with differing sensitivities to light wavelengths. In other words, it's pretty much saying that you have three different cones. There's three different types of cones in your eye. One cone is specialized to wavelengths of red, one cone is specialized to wavelengths of green, and the third one is specialized to the wavelengths of blue. And that all colors are created by the additive mixing process. So depending on the number and types of receptors that are activated due to the wavelengths, then that determines the color that we perceive. So why we like this theory is it explains color blindness. Because most people who are colorblind are dichromats. In other words, they are sensitive or they're missing one type of cone. So there's 3 types of dichromats. There's red, green, or blue insensitive dichromats. In other words, they have trouble processing red, trouble processing green, or trouble processing blue. Trichromats are normal, meaning we have 3. Dichromats would be color blindness. And then there is monochromats as well, which means they only see one color, or they only have one working cone type. But most color blindness is dichromats. So, this is a typical test for color blindness. So there are numbers in the middle of each of the circles. If you can't see the numbers, then you're probably colorblind. And usually people will be able to, that are colorblind, will be able to see the number in one of these circles, but not the other. And this is how we determine what type of dichromat you are. So it tests for color deficient vision. So this first color here tests for yellow-blue color blindness. In other words, people that can't tell the difference, or they're missing that blue cone, because the number in the middle here, 92, is in blue dots, surrounded by purple. And people don't have the proper blue cones or blue processing cones, then they're not going to see this bright blue of the 92, and it's going to end up looking this kind of purplish, grayish color, so they're not going to see the number here. Now the second one is for red-green color blindness. So we have green dots all around it with red and orange dots in the middle here, making up the number 32. So again, so we can figure out, if they're missing the red, then they're going to actually process these, the 32 as green. And if they're missing the green cone, they're actually going to process all of this surrounding as more of a reddish color. So the dots in the pic are equal brightness, and the color is the only available cue for perceiving the numbers. So everything else is the same except for the hue. Now with color blindness, a red-green colorblind is usually the most common. So red-green blind person will confuse a blue and purple because they can't see the red element of the purple. So if we look up here, again, we've got red, purple, blue pens, but a colorblind person may see this image on the right, where you've got kind of this like brownish color instead of pink, and then there's 2 blue pens. And that's again because purple is a mixture of red and blue, and if they can't see red, then they're not going to be able to make this additive connection between the red in the purple being different than the blue in the purple and the blue pen. Now there's another theory we need to talk about, and this is the opponent processing theory. And this is that the human eye has 3 types of receptors with differing sensitivities to different light waves. So this is saying that instead of having 3 cones and 1 cone is responsible for red, 1 cone is responsible for blue, 1 cone is responsible for green, this is saying that well, there are three types of cones, that each cone is actually responsible for two different wavelengths. So one cone is responsible for red and green, one cone is responsible for blue and yellow, and then the other cone is responsible for black and white. In other words, how that works is the eye, or the cone that's responsible for red or green, or red and green, is either always seeing red or green. So it's like a switch. It's either red or green. It's never both. And same with blue or yellow. It's a switch, so that cone's either tuned into blue or yellow, but it doesn't see both. And then same with black or white. And what the opponent processing theory does is that explains after images. So this is a great example here where this is an image of the Canadian flag, obviously, but in what would be the opposite or the off settings for the cones. So remember, one cone is red or green, so the parts that should be red in the image are now green. And then another cone is black or white, so the parts of the flag that should be white are currently black. So an after image is a visual image that persists after stimulus is removed. So a great experiment you can do here is get a blank piece of white paper and set it next to your computer. And I want you to stare right here at the dot in the middle of this image for a good 10-15 seconds, and just stare at it, unblinking, and then really quickly look at your white piece of paper. Now, if you get an after image, then what you'd see when looking at your white piece of paper is you would see the correct image of the Canadian flag. So anything that's green would turn red, anything that's black would turn white. And that's because you're looking at this image, and then when you change or you look away, then what you're seeing is an after image, or kind of the cones in your eye turning off or turning to the other setting. And so you'd see an after image of the opposites of each of these colors. Another theory that's very important is dual process theory. And this combines the two theories. It combines the Trichromatic Theory and the opponent processing theory. And this says that there's three types of cones, and each type is sensitive to different wavelengths. So pretty much you do have it says that the cones are red, green, blue, but then the cells that the cones talk to are split into three different types. That the cells are split into red-green cells, blue-yellow cells, red-green cells, and black-white cells. So you have three types of cones, but then you also have three types of cells. So that's what the dual process theory says. It's pretty much the best of both worlds. Now, the last thing we're going to talk about with the vision perception is depth perception. So this is the interpretation of visual cues that indicate how near or far away an object is. And our cues can either be monocular or binocular. In other words, from one eye or from both eyes. So monocular depth cues are based on image in either eye alone. So again, this is one eye. So we can do this using motion parallax, which is the relative motion of the object across the retina, so how it's moving, as well as pictorial depth cues. So this is looking at the linear perspective, texture gradients, interposition, relative size, height in the plane, line, and shadow. So in other words, its size compared to stuff around it, how things look just using one eye. So again, you can try this by closing one eye or covering one eye up and look around and see, if you can tell how far away something is using just that one eye, and then what's helping you figure that out. And then you can open up the second eye and notice what things are different with figuring out depth perception with one eye versus both eyes. And both eyes would be binocular depth cues. So this is looking at differing information from both eyes. So when information from the left eye differs from information from the right eye, that can actually give us cues about the depth of something, because we can use that difference to measure the depth. So this is retinal disparity. So objects project images to slightly different locations on the left and right retinas. And then we kind of use that information to figure out the difference. And then we have convergence, which is the sense the eyes converging towards each other as they focus on closer objects. So things that are farther away, your eyes tend to look, they're more looking straight forward, but when something's closer, you kind of go cross-eyed. And so that's what convergence is. That's kind of that cross-eyedness by trying to focus on something that's much closer to you. So that is it for the visual system.